Thank you everyone for being here at 4 p.m. on the last day of the conference. So you guys rock. My name is Ahmed Elmokadem and I'm a senior scientist at Metrum Research Group. And just one thing to get out of the way before we start, for my son and wife watching online. Hi. So I just made their day. All right, so let's start there. So open science, immuno-oncology, QSP modeling using open source Julia solvers. So the work I'm going to be discussing today is actually a group effort. All these people are involved. These are people from my group at Metrum Research Group, the Translational Systems Pharmacology Group. So let's go back to the title here and do some definitions. QSP, Quantitative Systems Pharmacology, what is that? Well, it's the study of the quantification of what the drug does on the body, like the effect of the drug on the body in a mechanistic way, right? So if you give a subject a drug, hopefully it does something, right? Hopefully it does something. So the mechanistic representation, quantification of what it does, this is systems pharmacology, in addition to the dynamics of how the drug is transported or distributed in the body, okay? So immuno-oncology, so oncology, cancer. So we want to treat cancer, right? So when people started looking at a system that is efficient in picking its target and eliminating the target, right? They found that this biological system already exists, which is the immune system, which is very efficient, right? Most of the time, okay? So this is learning by example. So can we use components of the immune system to help treat cancer? Right? So this is immuno-oncology, right? In a nutshell here. So this is just a representation of what we're going to be talking about. This is just to give you a taste of what these systems might look like. So I'll be going through, there's going to be a case study that I'm going to go through, like a specific example of how this immuno-oncology system can be applied. But the main focus will be like on the Julia. How did Julia help us here? How does it help us, and how does the Julia ecosystem help us build such models and simulate from these, okay? And hopefully also make a case for open science along the way. So who are we? We are quantitative scientists assisting small biotech and large pharmaceutical companies to develop medicines, right? This is our purpose. How do we do that? Well, we use modeling and simulation, right? So we build these models, statistical, mathematical models, and integrate the preclinical and clinical knowledge that we have about a certain therapeutic agent and disease, and to see how does this therapeutic agent affect the disease, right? Can we help in decision-making along the way using modeling and simulation? So something here that I really liked about Metrum even before joining is that Metrum is for open science. Like we try to push, contribute open science as much as we can, okay? So if we have a tool, we develop some of these tools to use internally. If a tool will be helpful to the community, we try to push it, like we validate it and we push it to the community so that anyone can have access to it. Because we believe that this is how science develops, right? Without open source, without publications, there won't be any science, right? So we try to do that. And I try to make the distinction always between open source and open science. So we've seen a case in a previous talk about how this function that was open source, it was available, but really it wasn't reproducible, right? So open source is the first step in open science. It's just one component. It's the beginning of the work, right? So you have to have enough validation, enough documentation, a way for the knowledge to flow. Right? An easy way for a flow of knowledge. And we think that Julia is a pretty good tool to do that, okay? So why did we select Julia for our primary systems pharmacology production platform? So we come from our background. So all of our work used to be R, right? And now we're shifting to use Julia for all of the systems pharmacology group, for all of the work that we do in our group. So why did we do that? Well, we needed a fast, scalable, and reproducible platform that we can build our models in. It has to be efficient. It has to be capable of handling larger systems, right? It has to be smooth, like it has to handle stiff, non-stiff equations, right? Because most of the systems that we have are stiff. So there's also the capabilities within the SciML ecosystem that you can automatically switch between non-stiff and stiff, which is great because it also saves time. Multi-scale spatial. So spatial can be an important component here. If you're looking at immuno-oncology, right? If you're looking at a tumor like biological system is not two-dimensional. It's not one-dimensional, right? It's a 3D structure. It's a spatial structure. So including a spatial component to our system could be very helpful. Like we could benefit, and our predictions could benefit from that, which is something that you can do in Julia. Like you can use Modeling Toolkit with a symbolic representation of a PDE, and you can integrate your work this way. Agent-based modeling. So a tumor microenvironment and tumor cells, they are not homogeneous, right? They are heterogeneous systems, right? Some would respond to a treatment, some wouldn't respond to a treatment, so there is some sort of probability there. Okay, so agent-based modeling could help us also there. Like if this is a question that we want to answer, right? So we can use this sort of thing in Julia. So Julia has a package agents.jl, which I think is great, and it helps a lot being able to mainstream the defining of an agent-based model. Bayesian models. So quantifying your uncertainty, right? This also could be a very important aspect of your analysis. You have a model, you're making predictions, but how certain are you about these predictions? How certain are you about some parameters in the model? Okay, so Bayesian inference. So we can easily also use the SciML ecosystem, ordinary diffie-Q or an ODE problem, and just plug it in Turing model function, right? It just works. Okay, so the composability of the ecosystem is pretty remarkable. I would say something else, like you would look at this system here. So this is just an example of the immune response to a tumor, right? So this is the model. So you can see a lot of nodes and edges, right? So ideally, you would have information and data about all of these nodes and edges, right? But almost always the case that there's something missing in your knowledge, okay? And hence UDE, universal differential equations. We heard a nice talk yesterday about applying universal differential equations in systems biology. Same thing applies here. Like if there is some part of the system that you're missing, that you just don't know, right? Maybe you can stick a neural network in there, learn the neural network. Maybe even you can do symbolic regression and learn what that missing term is. At least it's gonna direct you towards what nodes are impacting this missing thing, right? So this is all pretty nice, and these are all nice things about Julia that we like, and that's why we integrated our systems pharmacology group to use Julia. We also, because we didn't want to ditch R totally, right? So you can also use R and do R coding within Julia. R call works pretty well, at least for us. Like it worked pretty well so far, okay? So, yeah, so we already have a lot of published stuff. So we tend all of our publications, we have this associated GitHub repo with it. All the code is provided. And this is an example of code that we have out there. We have this open source Julia production code for monoclonal antibody PBPK model. A PBPK is a physiologically based pharmacokinetic model. It monitors the distribution of antibodies in the body, okay? So we were able to translate some of the code that was published in this paper, and we translated it into R and Julia, okay? And we have this repository that you can see both of these codes out there, okay? So just case in point here. So if you look at both codes, they are doing the same exact thing, right? And we validated that. The R code is about 6,000 lines, so it's a huge model. The Julia code is about 800 lines. So that's a huge improvement, right? It's much better to write and it's much more readable. And a case for open source here, we actually used this code, so the R version of it, right? So we used it during the pandemic. So during COVID, we collaborated with Eli Lilly, developing the first monoclonal antibody to go to clinical trials in the world. And it was crucial that this publication, so we had a great appreciation that this publication was open source. And it was very well documented. Okay, so we were able to grab, and actually I don't want to speak to say something wrong here, but I believe that they also shared some code, Berkeley Madonna, if I'm not mistaken, right? So don't quote me on that, but I believe that's true. So it was very straightforward for us to take this and to help in the decision making. We were running against time at that time, so it was a frenzy. And we were able to use that to help in candidate selection. We had multiple candidates, so we were able to help in candidate selection. And the first in human dose, we didn't have any other data. Like we wanted to say what would be the dose to give to a human to go to clinical trials. And we were able to do that within the matter of months, which was remarkable, right? And it was all possible because of that open science mentality, right? So we also have in the process developing open source immuno-oncology models. So this is coming out of the pipeline soon, right? So keep an eye for that in our GitHub repository. So the example that I'm going to be talking about is the ADC. What is ADC? It's antibody drug conjugate. All right. What's antibody drug conjugate? We said that the immune system is pretty good at picking its target, right? If you give a drug, like in chemotherapy, these drugs are pretty good at killing cells, right? These drugs are pretty good at killing the tumors, but they're also pretty good at killing all other cells. So the specificity is important here, okay? So what if we have this drug and associated with some linker onto an antibody that is designed to target an antigen on the tumor, okay? So that helps with the specificity, right? It also helps with the half-life because antibodies have longer half-lives, so the drug can remain there for a while, okay? So how does that work? So you have the antibody and some drug bound to it. An important factor in the creation of these molecules is DAR, which is the drug-antibody ratio. Usually it's 1:8, and there's a whole like branch of literature about how to design these things. So let's say that you have associated two drug molecules to this antibody, and then the antibody goes around, it finds the antigen on the tumor, and then binds to it, gets internalized. Now, two things could happen. The linker that binds the drug to the antibody could break within this endosome, or it can get recycled, right? Actually, a third thing could happen also. The endosome could mature or transfer to lysosome where the antibody gets broken down and the drug is released. Okay, so in both of these cases, the drug would be released. Then the drug would go to its site of action. Let's say the DNA. It goes to the DNA and messes with it. Okay? But also this drug could diffuse out of the cell. Okay? It could also diffuse out of the cell and gets diffused into a neighboring cell. Okay? And this neighboring cell might not have this receptor, right? But the drug is a small molecule that diffuses. That's what they do. Okay? This is called the bystander effect. Okay? Which is something that could increase the efficacy of the drug. It could also potentially increase toxicity, right? So there is a balance here to strike. So these are the key mechanisms that I've already discussed here. The drug itself is referred to as the warhead or the payload, linker and antibody. So these are the components. So as a motivating example, we're going to talk through the ADC modeling. So this is work that has been published already also. So again, open science. And usually how the progression in drug development goes is that we have in vitro data, then goes into the in vivo animal studies, and then ultimately human clinical trials. Okay, this is how it usually goes. So this model would recreate or would characterize the in vivo data. But as an example, we just focus on the in vitro system. We're assuming that we have an in vitro system that we want to model. Okay, we want to characterize the in vitro data that we're seeing. So let's take a minute here to just go through the typical ecosystem, Julia ecosystem that we'd use. Differential equations, of course. Modeling toolkit, of course. So data frames meta. So data frames is an excellent package, right? But coming from an R background, we're used to the tidyverse, if you know about the tidyverse language, and data frames meta is pretty close to that. So I personally find data frames meta to be awesome, an awesome tool. CSV for the transfer of knowledge. Plots.jl, we use that mainly for basic plotting, and then for more complicated plotting, we use Mackie, which is great. Algebra of graphics is also pretty close to ggplot2, which is the plotting package in tidyverse. Component arrays is pretty awesome because it really makes it easier to define the parameters, to define the variables, and to be able to index by name. So that's a huge benefit, especially if you have larger systems that you can't really keep track. Optimization.jl, of course, with all the optimization tools that are available in there, and Turing for the Bayesian inference, right? So this is what usually you would see if you open any script that we have, like the starting thing. So SciML, open source software, scientific machine learning. We are very fond of SciML ecosystem. You can see the sticker here. So Metrworks is our cloud computing system. So we already have ways to navigate through the Visual Studio Code as the favorable IDE for Julia on our cloud system. Additional resources, you can find the repository for PBPK modeling, a tutorial that we had to do PBPK using R. And bamlanivimab. This is the drug. This is the monoclonal antibody that we developed. Nobody asked us about the name. So bamlanivimab. Okay, so PBPK paper that's out there with the code that's associated. So this is the model. This is how the model looked like from that paper. So this is a scheme from that paper. And you would look here, this is the PK part of the model. The PK means the pharmacokinetics. This is how the drug itself, which is the ADC, would transfer between different compartments. Now, this is a very simple model. If you were here for my talk yesterday, you've seen the PBPK model, all of the different organs there. This is a much simplified version, right? So this is just two compartments here. And you have a component for the ADC and a component for the payload, because the payload could dissociate. It will have its own PK properties, right? If you're also here for my talk yesterday, you also know that I'm fond of my cursor, zooming cursor, so I'll be using it a lot. Right? So just heads up. Then the drug gets diffused into the tumor microenvironment. Then we have here two different types of cells. Cells that express the receptor, that highly express the receptor, others that have low expression of the receptor. This is just the experimental conditions, and everything that I explained is happening inside. Okay, so if we're talking about in vitro, so this is in vivo, because this part here, the PK, happens in vivo, in the in vivo system, where the drug is ultimately cleared, right? If you're talking in vitro, then you won't have this component. It will only be this part. So, and that's what we see. So I'm not gonna go into details. So this is a dissection of every part of the model. So this is the in vitro system. So you have the antibody binds to a receptor, can dissociate from the receptor, gets internalized, the endosome to lysozyme. You can have breaking of the linkage of the linker. In the endosome, you can have lysis of the antibody in the lysosome. In either case, the drug gets released. This is a target plus cell that has the receptor, but the drug then diffuses out and can diffuse back in a neighboring cell that doesn't have the receptor, like the bystander effect. So yeah, I'm not gonna go through these. These are just details about how the model is actually being built. So you can see the code. So that's not a problem. So let's skip right to the end. So yeah, now that you have this model, you can simulate all different sorts of things, right? So you can simulate, like, for example, target occupancy, how much of the drug is bound to the target of interest, right? As your PD measurement or pharmacodynamic measurement. Then you can scale this up. You can scale this up to the in vivo level. So what if you want to see what was going to happen in a xenograft mouse, for example, that has the tumor? Then you can model this and you can run simulations. You see that the tumor growing here without any intervention. If you give the drug at different doses, you can have different effects, right? Here's the same thing, and here was a conclusion out of the paper that if you give the doses in fractionation, like if you fraction the doses across some time, it will give you a better result than if you just give the dose at once. So just a heads up here, we are going to be at this conference, which is a pharmacometrics conference, American Conference of Pharmacometrics. That's coming in November. We have a workshop there, Open Science, Immuno-Oncology. And we also have a couple of packages coming out in this open source package suite to Julia to facilitate QSP modeling and simulation. And credit goes to Tim Nab, who did the groundwork on this package. So this is just a taste of what this is going to look like. So we're going to be rolling it out, working our way towards the conference. And you can see that it's kind of pretty close to how you would define your stuff in SciML. But you have these convenience macros. So you can define an init block here where you have the parameter values. These are initial parameter values. So you can change the parameter values as you go. And the initial values for the variables. And these are the differential equations. Right, so this is how you would define your differential equations. So another package that is more specific. So you can see that this package can be more like general purpose because any ODE-based model you can easily work through here. And our main thinking about having this is that we wanted to recreate the features that we already have in another R package, which is MRG Solve, that we also created in Metrum, like Kyle Barron. And we know it works. It has been there for a few years now, and we know it works, so we wanted to recreate that here. So yeah, that's it. Thank you so much. And please, this is my email if you want to get in contact. And yeah, I'll be happy to take any questions you have. Thank you. Was everything that clear?
Just a short and easy question. Just to get an impression of the complexity of your models, how many states do you have? What are typical simulation times? What is the scale you're talking about?
Yeah, big, but on top of my head, I don't know how the number of ODEs.
Approximately.
Like you have, for example, this PBPK model, that's 6,000 lines in R.
Yeah, but not code lines, but states or simulation times.
A lot of states. So if you have, like, for example, 15 organs, you divide each of these organs into like 4 or 5 subcompartments. And there's also the blood compartments. I don't know the combinatorics on this. I have no idea. Yeah. Okay. But yeah, parameter-wise, yeah, it's a lot. Yeah. So this can be huge. Also, another feature that we like in Modeling Toolkit is the composing. So composing different models. So that could be also very useful here because you can modularize your models. You can have a QSP model. You can have a PBPK model. Join them together with a linker, right? So that's also something Modeling Toolkit would do very, very easy to do. So yeah, I'll check the number of variables and I'll let you know.
Thanks.
No problem.